Swayam Prabha. Digital India. Educated India.
Hello everyone. Now we are discussing the different types of yarns and fabric structures for cut protective textiles. So, along with the different types of fibers, high performance fibers, we need different yarn structures and also different types of fabrics like knitting, knitted fabric, woven fabric, and also the non-woven fabrics. Non-woven fabrics are used for some specific purposes. It has some speciality which the woven and knitted fabrics cannot provide. So, that is why the woven, along with the woven or knitted fabrics, non-woven fabrics can also be used in combination with maybe knitted or woven fabrics for additional protection. Non-wovens are produced in different ways, basically different processes are there. Here directly fibers, from fibers we can produce the fabric. Fibers are laid in the form of web, and there are different types of entangling the fibers are there, that is by mechanical entanglement, thermal or chemical entanglements are there, and specifically non-woven's function for cut protection is, you can see that for protection function is basically due to the, it provides bulk and cushioning and enhance the friction path, that is important, where you can see in case of knitted or woven there is a thickness is less for same GSM for same fabric, where in case of non-woven we can produce a thicker web, okay, for same material. So, thickness is more. So, in for cutting with a sharp object like knife, here due to the bulk and cushion it enhance the friction path, okay. That means it delays the entire cutting process, which helps in slash or abrasion which and spread the local contact pressure under the blade. So, under the blade whatever localized contact pressure was there, due to this friction path and cushion, this gets spreaded over the wide area. So, that means the contact pressure is reduced. Next function is that it is a isotropic behavior, which is very important. In case of woven fabric, as there are only warp and wave directions are there, their actual behavior is directional. But in case of non-woven fabric, it allows the isotropic behavior. So, for all the directions it will be, its performance will be same, so which are absent in woven or knitted fabric, and this is cost effective because non-woven can the production speed is much higher than knitting and oven, and also you do not have to produce intermediate yarns. So, cost effective, and we can produce in wide width for different applications where wide width are required. So, in those applications we can use this non-oven. So, it is a basic advantage is that it is a isotropic behavior, and third is that it enables laminates. So, that we can use that neat plus non-oven plus coating. So, this type of multi component protection we can use. So, knitted or oven can give the protection, and the non-oven can give the cushioning, and it will delay the cutting process. So, laminates can be produced for progressive energy dissipation. Okay. So, that is why here it is giving protection, and this is energy dissipation will be there. Now, we are going to discuss different cut resistance test methods. So, there are different standards, but effectively there are two methods we follow. One is TDM tester, another is the coupe method. So, there is a coupe method is there. So, the cut resistance of material is challenging to measure due to complex failure mechanism. So, that measurement is very complex. It is not straightforward like a tensile testing or abrasion testing. Here mechanisms are complex, that is mechanics. So, that is why even the data interpretation is not also simple, and we will try to understand the mechanics and the data interpretation. If we see the early testing for firefighters gloves in 1950s, they used a 60-degree blade in static, like slow wipe under load, and a dynamic, that is blade drop impact cut was used. So, 60-degree blade slowly moving, static, and also dynamic, certain blade is dropped, drop impact cut. So, that type of process was used, but that process had many drawbacks, that was not acceptable and not used at present. Then static cut tests have since evolved in modern standards. So, this slow wipe cuts are used, but with modern standards are there. The standard methods are either ISO method, ISO 13997, EN 388 and ASTM F 2992, and these are the methods typically that is recognized at different regions of the world. Like EN is basically in European standard, ASTM basically it is a in US the people use, and ISO is also enter Europe, they use these methods. And then dynamic cut test, free fall blade impact led to other standards like ISO 13998, which we are not going to discuss here, cover here, because these are some special testing. Here we will be covering two tests, one is TDM and one is coupe method. So, historically the Europe relied on EN 388 which is coupe method since 1994, still we are using, and in North America ASTM F1790 since 1997. So, after all evolution, so these are the methods people used to use, and by 2016 there was some changes. So, then harmonization begins. The EN 388 was adopted, they adopted ISO 13997 method, and ANSI method like American National Standard Institute cut level were revised and aligning the global practices. So, there were different changes with the time. Now, let us try to see the difference between ISO method and ASTM method, ASTM F2992 and ISO 13997. So, ISO method actually predominantly used for the product certified in Europe. So, mainly it has to be certified in Europe if you want to use the product in for Europe. So, you have to go for ISO certification. The CART score is a part of the EN 388 standard. So, here it indicates the letter by A to F, F being the highest cut protection, and in ASTM method the sole cut resistant test method was used to produce the product certified in the Northern America. So, the CART score is a part of ANSI and ISEA 1045 standard, which indicates the level from A1 to A9, A9 being the highest cut resistance. And these are the differences, okay, and the similarities are you can see the similarities here for both the methods, ISO and ASTM methods. The both standards specify the test method to determine the amount of downward force, and that is important. So, amount of downward force required, that is in newtons or grams, for a straight cut. So, okay. So, this is the method and here is the cut. So, we want a downward force, amount of downward force in centinewton or gram that required to have straight cut, straight sharp blade cut through a material after traversing a specified distance. So, that means let me explain here. Suppose this is one anvil where the specimen is placed, cut protective specimen is placed. This is the fabric is placed, okay. this is the fabric. Now, we have one blade, this is a blade. The blade moves in to and fro, maybe one direction it may move, it is moving say to and fro. Here we will say this is a movement. Now, we can change the normal load, say gram force or Newton. We will change the gram force, we can change. So, for a certain load, suppose that it is moving, and as soon as there is a cut formation, there will be electrical connection between anvil and that support and the fabric, and that immediately it will stop. There is a hole formation, but before hole, that knife will move at a certain distance, it will travel at certain distance, this is moving for certain distance at certain constant load, okay. And here the specified distance is typically 20 millimeter. Suppose for a load of 10, the distance is travelled before cut is maybe 30 millimeter. In that case, so we cannot take that 10 say gram force or something, we cannot take that load. So, we have to increase the load to say 11 gram force, and then if we increase the load, at that case what we found, it has become 27 millimeter, 27 millimeter. That means 27 millimeter will not be helpful, because we have to reach 20 millimeter. In this way, we will keep on changing the load, and we may or may not reach the value 20 millimeter. So, we will get different load in Newton or something or gram, and we will get the cut through distance. And then we will plot, and from the plot we will be able to measure, calculate the load value for a 20 millimeter, that specified distance. That is why this process is not that simple, it requires a long experimentation, okay, that we are going to discuss here, how this test is carried out. After that is, we have to measure after travelling a specified distance. As per the standard, it is a 20 millimeter. The equipment here is basically, it is a both these types, okay. Here in this ISO and ASTM, this methods we use the method which is called TDM method, TDM 100, tomodynamometer instrument is used, where this performed using the same type of machine. So, tomodynamometer is used. So, both these standards are used to evaluate the materials like those in cut resistant gloves or sleeves for protecting against the sharp objects like knives, glasses, sheet metals. So, this both the methods they are used for the protection against sharp objects like knives, glasses, sheet metals. Okay. And this is basically it is a slow motion quasi static method. The differences here are their methods are same, while the overall methodologies are similar, there are minor differences in their procedure, specific procedures are there, such as how the machine is balanced, how the data are analyzed. The ASTM they analyze actually in the form of the analysis in the form of the linear feet like logarithmic data is required, whereas the ISO direct the data we use that we are going to discuss. So, ASTM follows the linear feet of logarithmic data, but ultimately we will see their results are same. And also how conductive materials are handled during testing to prevent false reading. As we have discussed, any conductive material like stainless steel, they can result the false reading. So, how these conductive materials are handled, they are actually different for these two types of system that has been specified. So, the differences are how the machines are balanced, how the data are analyzed and also how the conductive materials are handled. Okay. Scoring, the primary difference from an end user's perspective, it is classified at and reported in differently. So, that classifications are different, although their testing methods are same, and that is why classifications are different means their the ratings are different. Now, cut resistant scorings or ratings are different. Now, let us see for ISO 13997, that is EN ISO 13997, that is cutting loads are used, you can see, and in ASTM method the ratings are A1 to A9, okay, and in EN method it is A, B, C, D, E, F, A to F. So, F being the maximum cut protection and A9 being the maximum cut protection. So, here in ISO method, if for the 20 millimeter cut through distance, if the load is 2 Newton, then we will call it as A1, okay, and if it is 5 Newton, then B, 5 Newton, between 5 Newton to 2 Newton and 5 Newton and below it is B, and up to 10 Newton, sorry, 2 Newton and above, 2 Newton and above it is A grade, 5 Newton to 10 Newton it is a B, 10 to 15 C, 15 to 22 E, and 22 and 30 it is E, and 30 and above we will call it as F, which is maximum cut protection, very high cut protection. Similarly, for this ASTM, if it is more than equal to 200 gram force, it will be A1. Similarly, A9 is the maximum cut protection. If it is more than equal 6000, then it is A9. So, if we see in ISO method F grade and in ASTM method A9, they are basically equivalent. Okay. But the testing methods are same, TDM testing methods are same, their scorings are different. Now, let us try to understand the testing protocols, and first the background and significance we will discuss. For ISO method, it is basically for protective clothing, determination of resistance to cutting by sharp object, which is published in 1999. Initially it was optional, which is referred in EN 3988, and it was a limited use until 2016, when EN 388 mandated it for certain material. So, that is it was initially it was limited use, after that this is mandatory. So, ISO 13997 is now mandatory, EN 388. So, it is globally adopted, now widely recognized as a reliable test for high performance cut resistant material. Particularly it is important in Europe after EN 388 2016, actually 2016 it has adopted, particularly important in Europe after EN 3888 2016 it is adopted, and also used in Japan and different industry section. So, that at different industry sectors we use this, it is globally adopted method. And thermodynamometer TDM 100 is the instrument which we use, okay. And this machine was developed in Canada, Canada's RGI company, or developed in IRSST, and this thermodynamometer means a device for measuring the cutting force, that is important here. Now, the key idea is to determine the force required to achieve a 20 millimeter specified length of cut stroke through the material. So, that is important, the force required to achieve a 20 millimeter cut stroke through the material, that we have already explained earlier. This test was introduced to overcome the limitation of Coupe test, that blade blunting issue is there. So, in Coupe test it is a blade blunting issue is there, but that was actually some procedures are followed to counteract, to actually minimize the blade blunting issue, that we will discuss. which is called blade dulling, by using fresh blade for each cut and varying loads. So, here the frequent blade change is required in TDM. So, for each cut we need to use new blade. Even for varying load, for a certain load we are using one blade, and for if we change, we have to change the load, and next load we have to use the other blade. So, fresh blades are used, number of blades required here is very high, and also it is a time consuming, and coupe method we will discuss. Here the this blade change is not that frequent, but here blunting issue is there in coupe method. So, equipment, if we see here, that is a blade holder and this is cutting blade, the specimen is here, sample. Now, conductive tape is placed below the sample support, because it should not strike the sample holder, otherwise it will damage before it touches. The conductive tape is there, which is placed below the specimen, so that immediately the instrument stops, okay. And sample mounting adhesive tapes are there. This is the sample mounting and here is the sample. So, sample mounting adhesive tapes are used, both side adhesive. So, that is placed first on the sample holder, then over that the conductive plate and specimens are used. This is the schematic diagram of TDM done on TDM tester, 100 tester. A straight edge blade is pressed, this blade is pressed on the fabric sample holder by certain load. This load is changed the blade is drawn across the sample in a linear motion. Okay. This is blade is travelled in a linear motion under certain load at a constant speed. Usually the speed is kept 2.5 millimeter per second. It is very slow speed, this moves under specified normal load. Certain load is kept and it will move till there is an perforation, there is cut on the specimen, and the sample holder shape is curved because to have proper cutting force. If it is flat, then the force will be distributed and the cut portion will be longer. We need a particular cutting portion, pointed cutting, not actually pointed, because it will be a low cutting way, length will be there. Blades and calibrations, you can see it uses standardized replaceable razor blades are there. So, standard blades are there for cut resistance. Each batch of blades is calibrated on a reference material under load. The average cut through distance should be 20 millimeter. So, for each batch we have to calibrate the blade first with the reference material. Now, this calibration is basically it is a D0. Okay. One reference material has to be used, typically maybe a canvas cloth or something. This calibration is actually D0 ensures the uniform baseline for the blade sharpness. The calibration we have done with the standard reference material. So, D0 is the this is a calibration distance. Now, we have to mount the material. The sample is secured on the carved anvil. This is the anvil. If the sample contains conductive yarn like stainless steel, you have to see, we have to know the whether the sample is it contains the conductive yarn or not. If at all it is there, an insulating film is placed under the sample, okay, to avoid the false cut through signal. So, here insulating films are used if there is any that stainless steel is there. Now, blade use, a fresh blade is used for each cut trial to eliminate the blade dulling between test. Blade may get blunted during the test. So, to have uniform the standard value. So, we have to change the blade after every application, after every use. And which ensures the consistent sharpness for every cut, because blade blunting or dulling affect the cut through distance. So, that to avoid this, so to have consistent sharpness is required to avoid this wrong interpreted wrong result. So, we keep the consistent sharpness by replacing the blade every time, and which improves the reliability on cut through material. So, to get correct result, we should replace the blade. Now, first is calibration cut. For any test, we have to have some calibration cut through. Calibration cut, what is that? Perform a trial cut to verify the blade condition. Okay. Expect approximately 20 millimeter cut length. So, some preliminary cutting has to be done, trial cut, then test cut. So, there the blade has been that calibrated here, the system has been calibrated. Now, they apply the selected load on the blade. This is the test cut is recorded. Record the distance. So, selected load is there, load we have recorded, and then the cut through distance we have recorded. Record the distance travel at the cut through. So, when cutting is there, at which distance the cutting take place, that distance is recorded, and the load is recorded. Next is the this repeat at various load. So, we have to repeat it, this load, and record the cut through. So, load is there and distance. So, 1, 2, 3, 4, 5. So, distance is recorded. So, here the standard is that at least 15 cut per samples across the load is required. So, we need at least 15 cuts per sample. Okay. So, we have to use a new blade for each data point. So, fresh blade for each data point. So, avoid progressive dulling. So, if we use the repeatedly the blade repeatedly, the problem would be that it will give the wrong result, because cut through distance will be longer for the same load. So, sharpness will be, it will be dull, it will be blunted. So, for to get reliable result, we have to use the fresh blade at each time. So, this is the total procedure. First calibration cut, then test cut for a particular load, then we have to repeat at least for 15 times, and then we have to change the blade after every use. Now, this is the system test protocol, is instrument, you can see where blade and blade holder is there. This is a blade and blade holder. Here it is a mandrel and connecting lever is there, where we can apply the certain load. Okay. This is a motor which moves the blade, and this weight. So, known weight is that, so we will change the weight. So, there spare weights are there. So, we will change the weight to get a plot. Okay. So, as per the standard, it is at least 15 different types of load we have to apply, and here is a controller. This is a controller. Now, the stages, if you see here, we are mounting the sample, fix the fabric with conductive strip and tape. So, we are mounting the sample. Next is the, we are balancing the beam and load is being applied. So, the load is applied, normal load here. So, we are installing the new blade. Next is the we are starting the cutting cycle. Blade moves at fixed speed, the speed we have already mentioned. Then auto stop condition we have initiated here. So, as soon as there is a cut, the instrument will stop without further movement, and the movement is recorded. Record the result, note the distance, how much distance it is travelled, and then we have to, the distance it is recorded here, and then we will reset it, make it 0 for the next test. This is the these are the different stages of testing. Now, if we see the actual video of running this instrument, in our lab we are doing this experiment. The tape, the double sided tape is being placed. We are placing this tape and now the conductive copper strip we are placing it. This is for to avoid the any damage on the anvil on the system. So, immediately this, as soon as it there is a cut, the instrument will start. Copper strip is placed on the this anvil, that is sticked with this double sided tape, gum tape. Now, on this anvil we will place our specimen. Now, this specimen is placed. This is the placing the and sticking with the gum plate. This is the system, and then we are placing this total entire system fitting with the instrument. This is the placing of the system, and now we are placing the fresh blade. This is installed and the direction has to be fixed. So, we cannot use any blade, this is specifically for this instrument. Now, we will apply the load. The required load is applied. Now, final test will start. Now the blade is moving, you can see. Now, as soon as it is there is a cut through distance is there. Now, here the load we have kept different sudden load. Now, here for the next test we will change the load, again repeat the entire thing will be repeated. So, after all this, so we are then noting the cut through distance according to particular weight. So, after changing the load we will repeat all these steps again. So, here through animation we can see this is the mandrel here, copper strip, both side tape, fabric specimen and blade. Now, try to see the both side tape is there, then the copper strip and the fabric, and then it is cutting. This is the system. Let us see once again. First both side tape, then copper strip, then fabric, and then it is ready for cut. Both side tape is coming, then copper strip, then fabric is placed, then cutting starts. So, this is the system stages of this test, and then we record the cut through distance, okay, CTD, cut through distance in millimeter for a given load, and as per the standard we have to repeat this test, this system for 15 times with different loads to get a plot. Now, we can see. So, calibration distance we have discussed earlier. Calibration, that is to ensure uniform baseline for blade sharpness. So, there is a standard blade was used, standard fabric was used. So, standard sharpness we know, that is the calibration distance, and the sharpness index of a particular blade we can calculate. So, sharpness index is the standard distance was, this is a 20 and calibration is D0. So, if D0 is say 18.6, then sharpness index will be 20 by 18.6, it will be 1.075. This sharpness index will be used to correct the distance, that is normalized distance. So, the normalized cut through distance is basically actual cut through distance multiplied by sharpness index. Like if actual cut through distance is 18.6, then if we multiply by 10 point, so 1.075 sharpness index, then we get the actual distance 20. So, normalized distance we can calculate by multiplying the cut through distance, actual cut through distance by sharpness index. So, sharpness index we have to calculate. So, the use of the common logarithmic form of cut through distance when performing the regression analysis has been found to provide the most reliable method for establishing the calculated load. So, logarithmic method as used by the ASTM. So, that is actually most reliable method is there, but normal cut through distance also with that also without logarithmic curve also we use. Now, data processing and result interpretation. Y dash equal to B 0 by plus B 1 x, which is a logarithmic method. In the logarithmic method we get the straight line, okay, and where y dash is the log transformation of normalized cut through distance, the log 10 yr is the normalized cut through distance, and if we take logarithmic value, that is y dash, and b 0 is the intercept and b 1 is the slope of the curve, okay, that is regression line, that we will discuss, and x is the applied load. So, for different applied load we can get the cut through distance and it is a log transformation. So, cutting load equation will be, so if we just rearrange this equation, it will be y dash minus b 0 by b 1. So, cutting load is x r, cutting load which is required to represent the this actually cut performance, which is basically it is y bar, which is nothing but log 10 y r is the normalized cut through distance minus intercept divided by the this slope of the regression line. So, x r here we calculate in terms of gram force. Okay. And y are the reference distance, that is 20 millimeter, that is the reference distance is required. For 20 millimeter, what will be the cut through distance? Okay. So, this is the, now what for y 20 millimeter, what will be the load, normal load. Okay. So, that load is the actually cut resistance value. Now, we can see this is the data we get from the TDM testing. So, there are different columns are there, and weight you can see that in column B it is a at different weight we calculate the cut through distance. For each weight we get the 3 readings of the cut through distance. So, for 400, 600, 800, 1000, in this way we get. So, total 15 data we can get here. Okay. This is only typical and then we multiply by the sharpness, that is I will go back here, that sharpness index we multiply to get the normalized cut through distance here. So, normalized cut through distance is there, and then we calculate the slope. Slope is B1 as per the earlier previous slide. I will go back to the previous slide. This is the slope 1, B1 is the slope. So, we can calculate the slope of this curve by from this between the this and this curve, sorry, between this is the normalized value, this is the normalized value, log value, we use the log, okay, log, and this B and E we calculate the slope, and intercept like E and B we get the intercepts which is B0. Okay. And then cut through distance is calculated by this relationship G5 minus log 10 20 by 20 is the cut through distance here, an actual standard distance. So, actual cut through distance is calculated. G5 is typically a value representing an upper limit, that is potential or specific value in the system G5, and G4, that the modulus of G4 is absolute value of the lower limit or coefficient or gradient. It often it is a negative, that is why modulus is used, absolute value is used. So, here if we see it is a cut through distance is coming out to be 614, but this from this curve, from this interpretation, it may be little bit difficult to understand. So, here if we plot the curve and plot the log curve, then the things will be very, very clear, and at this point we will stop here, but we will continue with this understanding in detail the interpretation and test protocol in the next session. Till then, thank you.